Black holes are intense gravity traps. When a star wanders too close, it gets violently stretched and torn apart by tidal forces, so extreme they overwhelm the star's own internal gravity. This gravitational disruption ripples across entire galaxies. In Centaurus A supermassive black hole has twisted the central dust lane into a prominent dark scar that spans thousands of light years. Observing these interactions is a unique challenge. Since a black hole absorbs all incoming radiation, it emits absolutely no light for a telescope to detect. To bypass this, the Event Horizon Telescope networked radio observatories across the globe. This coordination essentially turned the planet into a single Earth-sized sensor, capable of resolving the center of a distant galaxy. In 2019, this collaboration revealed the first direct visual evidence of a supermassive black hole in Messier 87. The image shows a fiery ring of gas orbiting a central, lightless shadow. This silhouette is the only part of the object we can actually see. To understand what happens beyond that dark edge, we have to move from observational astronomy into the realm of theoretical mechanics. Moving inward toward the center, we reach a region where standard orbital dynamics ail. At this close range, the inward gravitational pull becomes the dominant force in the environment. This spatial grid illustrates the Schwarzschild radius, the precise mathematical threshold where escape velocity exceeds the speed of light. Just outside lies the photon sphere. Here, the extreme curvature of space captures passing light particles, locking them into a permanent, inescapable circular orbit. Passing this spatial threshold represents a transition into unknown physics. Once light is trapped, our classical models of general relativity lose their ability to predict what happens next. Classical physics suggests that because nothing can escape a black hole, the object should remain static and dark for eternity. Stephen Hawking provided the mathematical evidence that challenged this static model. He identified a quantum mechanism, now known as Hawking radiation, that allows energy to slowly leak across the event horizon. This occurs when particle-antiparticle pairs separate at the horizon's edge. One particle is consumed, while the other escapes as radiation. This continuous quantum leak carries mass away, slowly shrinking the boundary over trillions of years as the object evaporates. This evaporation means that black holes are finite and mortal. They are not permanent fixtures of the cosmos, but objects that will eventually disappear. At the very center of a black hole, gravitational forces threaten to become infinite. Here, the fundamental laws of known physics cease to function. To explore these extremes, physicists use the Swampland program. This framework filters out quantum theories that are mathematically inconsistent with the intense conditions found inside a black hole. At research centers like CERN, these theoretical models are tested to see if they can reconcile quantum mechanics with the behavior of large-scale gravity. One major theoretical risk is the naked singularity. In some models of rapidly spinning or highly charged black holes, the protective event horizon could vanish, exposing the infinitely dense core to the rest of the universe. A naked singularity would destroy our understanding of cause and effect. Without a horizon to contain it, the infinite density at the center could lead to unpredictable physical events in open space. The weak gravity conjecture acts as a mathematical safeguard against this collapse of logic. This conjecture requires gravity to always be the weakest fundamental force. We test this using extremal black holes with maximum charge. To remain stable black holes instead of naked singularities, their outward electromagnetic force must outweigh the inward pull of gravity. If this conjecture is proven true, it provides a vital link between the physics of the very small and the physics of the very large. By pushing our current models to their absolute breaking point, these unseeable anomalies provide the specific data needed to bridge the gap between quantum mechanics and the cosmic scale.